Good afternoon. This being Switzerland, we try to start things on time. I think it is time. It is time, not quite, a few seconds more. But anyway, the important act is to follow. So this is a public defense of Eric Bezzam for his thesis. You can read the title. He will tell us about it later. For those of you who traveled, and some traveled from far away, I would like to thank in particular his parents, came from far away from California, and others are online from far away. So let me just explain the process here. At EPFL, the PhD, which is highest degrees that we give at EPFL, is done in two steps. There is a private defense, which is with a committee of experts, and that happened, I forget what. No, I want to insist, this is actually very important. It's not only about persuading experts, but also persuading people from the general public that some worthwhile research has actually been done. And so with this, I would like to pass over to Eric for the presentation of his thesis on public defense. Thank you.
Yeah, thank you, Martin, for a very kind intro. And yeah, looking forward to share this moment with you as I mentioned in the messages and in inviting you here. So thank you all for coming. So I'm going to present my thesis, which has a super long title: Robust, Generalizable, and Reproducible Computational Imaging, a Lensless Perspective. So I've done this in Martin's lab, which is called the Audiovisual Communications Laboratory, or LCAV, which you'll hear later on for short. And for my jury, I had Professor Sabine Zustrunk from the IVRL lab, two external experts, Christina from Cornell University, Ashok from Rice University, and Amir Zamir here from EPFL. So let's break up this chunky title. So what is computational imaging first? There's something that needs to be broken down there. So most of us are familiar with cameras. So actually cameras, yeah, sure. How about now? Test. I still hear on that one though, but okay. So cameras, so a lot of them, they're built to replicate the human eye. So if we look at the human eye, we have an iris in a pupil, which is essentially the entry into the eye. So what brings light in from the world into our visual system. And we have the retina, which is this sensitive part of the eye, which is capturing this information. So the very earliest cameras were actually built in the 1500s, and these weren't the cameras that we think of in our conventional sense, but camera actually comes from camera obscura, which is a huge room, so a darkened room. So the way they built the first cameras were putting a small hole, so like our iris and pupil, letting light through to collect on the other side of this darkened room. And then essentially over hundreds of years, we could perfect this and simplify this, miniaturize this into the digital cameras we now know, where instead of, let's say, some analog film or our optical nerve, we have a digital sensor. So it could be like a CCD is one terminology for this. So with this type of camera, we've already been able to do really crazy and amazing applications. Some of them just enhancing the quality of images, removing the blur of images, trying to zoom in into certain features, what we could call super resolution. And then let's say more higher level tasks that we've been able to achieve with these type of cameras are what we call computer vision. So maybe trying to classify things in object, segment things. You can think for autonomous vehicles, trying to detect if there's passenger or pedestrians or cyclists. So already with these type of cameras, we've been able to do a lot. And because of this, immediate use for such cameras, we've seen an explosion of them. So I can't even plot today's amount of cameras because it's 12 times the capped line that you see there. So there's been an explosion of cameras, like on our smartphones, in so many places. So a lot of these are not even being used by humans. So those are cameras, but what is computational imaging? So the idea of computational imaging is we're going to design both this camera hardware, so this thing that we've originally tried to mimic the human eye, but also the algorithm itself. Because as you can see with a lot of our cameras, they're connected to digital computers. So there's more that we can do than just that raw picture that comes from the camera, or what we would see directly on our eyes. So how can using a computer allow us to design new ways of seeing the world? So we already saw the human eye. We can look at some examples in nature. We have the eyes of insects, which have many little lenses to perceive the world around them. a funny example that I spoke about in my thesis of scallops. I don't know if many of you knew, but scallops have around hundreds of eyes along their shells, these little blue iridescent things. And each of those eyes actually has the structure of a telescope. So what you have is a lens and a mirror, which actually reflects it onto their sensor on this part of the eye. So they have this really complicated structure. And why do they need this? Hard to say, but what we know is that they need to be able to move around, something like this, to avoid prey that may be trying to fish at them, or humans looking for, sumptuous scallops to eat. But because they can move, that's why they're so meaty and tasty, scallops. So they're good. That's why thankfully they have eyes, which is good for human consumption. But anyway, I'm digressing. So the question that we're trying to get to is, do computers need human eyes? Because right now we've been trying to give eyes to computers, which are based on human eyes, but do they really need those type of eyes? So that's one of the questions we're going to look at. So that's where this lensless perspective comes in. So what is lensless? So actually, this camera obscure that I spoke to you about before was actually lensless. The very first camera was without a lens. So it was a small hole where we had some guy, looked kind of like me, I think, on one side, and we have to wait a long time to take a picture. That was a problem with these type of cameras. So one solution was, okay, we're going to make that hole bigger, and what we're going to add is now a lens, so now we can focus that light more efficiently onto that plane in the back. And then we can miniaturize this whole structure as well too. Another solution, maybe, if the problem was there's not enough light, is why don't we poke more holes into this camera? That way we have more light, right? But an issue with this is that we're going to get what's called a multiplexed image. So we'll see examples of this where instead of just one guy like this, you'll see many overlapping guys like this. So it's not something that we can like readily make use of, but maybe a computer can still use it. So this is the idea of what has been a core theme in my PhD called mass-based lensless imaging. So the conventional camera will have a lens, something like this, maybe quite thick, which is going to focus an image directly on that sensor. But that sensor could have been digital, could have been analog. By analog, I mean it could have been like some sort of film that we just look at right away, like maybe on your Polaroid picture cameras. But the type of camera that we're going to be looking at, that we looked at in this work, was a lensless camera, where we replace this lens with actually a super thin mask. So there's an example in here. So here's an example of one of those thin masks. I'll show it this way in the camera and then this way. So we can replace, the idea is this with this. So something a lot more compact. But as you see here, we get this mixed up image. What I called multiplexed, or what I'm going to say sometimes the lensless capture. And we're going to need now an algorithm to go from this to the image here. All right, so some ways that this has been used. As I mentioned, is one way is they've been able to miniaturize cameras. So this is work from other labs. You can replicate normal photography now with these type of cameras. You can do 3D imaging with these cameras, because what a lens does really well is focus on one plane. But actually now, since you remove that strict focus on one plane, we've broadened it to be able to do 3D imaging or refocusing at different depths. Or actually, if you have a special type of sensor, from a single picture, you can even reconstruct a full a high-speed video from that. So these are some examples from previous labs. So that's the lens perspective. Now we're almost done speaking about the whole title: robust, generalizable, reproducible. Okay, let's give an intuitive idea what that means. So we talked about this explosion of cameras, right? So these are lensed cameras. If I were to show you lensless cameras, it kind of looks something like this, a flat line. And why is that? Well, it's because such cameras are unreliable, maybe hard or expensive to build. You'll see some clunky prototypes I have here. So that was that other part of the thesis of when it comes to things. Next slide. Okay, robust, generalizable, reproducible. How can we address that issue with lensless cameras? Maybe have a little bump at one point in the history of camera usage. So that's breaking down the title, and some of the contributions, which we'll go over two of them that we've made in this thesis, were theoretical analysis of what makes it unreliable. So some of the noise or the errors that pop up when you use such cameras, an approach that we adopted to better address that type of noise. We'll look into an application now that you can use such cameras for, so some security applications. And then around this, so I mentioned it was expensive or hard to build. There was a toolkit that we built. Here we can see kind of a more final version of that prototype to make it more accessible, reproducible, and low cost. So I'll talk about that really quickly. So essentially this toolkit, we were able, sure. Oh, I didn't do that. That would have been useful for them. There we go. So a lot of the prototypes before for lensless cameras, they would have cost around a few thousand. So not something, let's say, convenient for, oh, I see myself on the big screen now, for your everyday person use. So one of our goals has been to bring it down to around $100. So using off-the-shelf components such as Raspberry Pi boards and sensors like these. So to make it more accessible for hobbyists or people on a tighter budget. And all this has also been packaged using Python to make it also open source and free software. And here I mentioned some of the parts we've 3D printed, so it's easy for others to then print it themselves. Here are some pictures of those designs and some metrics on that. And yeah, through this toolkit, I've been able to interact with quite a few universities, so that's been super cool during your PhD. I mean, collaboration is always important, and then just getting the feedback of people who found it useful or found ways to improve it has been super encouraging. All right, so the outline for the rest of the talk now. We did this long intro, so congrats, you made it through. Next, we're going to talk about two of these contributions that I mentioned. So improving the performance, so the reliability of these. We're going to talk about some of these security applications, and then I'll conclude the defense part of this presentation. So for improving performance, so this was work related to these three papers that I've listed down here. One of them, which, yeah, really grateful to receive the Best Student Paper Award this year at ICASP in India. So I mentioned these cameras, they don't give an image that you can see right away. So for example, we have this, let's say, image of what, let's say, leaves on a table could look like, what a normal camera would give as a picture. But because of this mixing, because of these multiple holes, we get something completely blurred like this. So this is what we would call, let's say, the imaging or the forward process. And in signal processing, when we have this type of mapping from something we like to something we don't like, we called it an inverse problem. And we want to essentially do the inverse of this process. So the way we do that is by setting up what we call an optimization problem. So we're going to take these different entities, give them fancy letters. So Y is this measurement. X is this thing we want to recover. We don't actually have the X, but for some reason we still put it into the equation. But what we're going to get is this X hat by minimizing this representation of the imaging process. So this HX is describing how an image is taken in a very simple form. We can call it's what we would call linear shift invariant or linear model here. So that's the forward process. So now I'm going to break things up for you a bit. So there's a dark secret for lens imaging. I've hyped it up a lot now, but there's something that you need to know. So another reason why we're not really using these cameras so much is because they're really sensitive to light. Light from outside, light from indoor. So here, most of the pictures you'll see of lensless cameras have actually been taken in very dark rooms. So it's not going away from that camera obscura in a way. So what happens is when there's, let's say, some light source in the room, what can happen is this already not so great image will get even worse. So we see that this image starts to break down in the presence of these unknown or unwanted light sources in the scene that we're trying to image. So we're going to look at some theory now. So just take a deep breath, and we're going to break it down. But this was one of the contributions. So we have this forward model, which we assumed this is what's describing our world. And we usually have to do this because we need to have a model which we can efficiently compute on a computer. We could try to represent the world as closely and as perfectly as possible, but we may not know all the parameters of the world, but also just may be too expensive to compute. So we make simplifications. And what happens is those simplifications are going to amplify this noise, which I didn't show you before, but there's this noise. And we already mentioned one of the sources of this noise is this unwanted light that's coming from the outside, but also noise that happens maybe due to imperfect electronics, so at the sensor itself. And what happens is when we use an imperfect, let's say, forward model, so before I assumed, let's say I knew this HX, but now I'm using an estimate. So when we usually put these nice little hats on top of letters when we want to say it's an estimate. So for this estimate, what I'm not going to be, the thing is when I actually do my inverse, I'm not going to be actually using the real H most of the time. I'm going to be using some wrong or estimated H. So that's what this H hat is saying here. And then when we plug things together to see, okay, what happens when I put H hat here? things get a bit messy, so bear with me. But there's going to be a mismatch error. So this is because we have this error in our forward modeling in the way we think we understand, or that we try to explain the forward process. We're going to have this amplification of the noise at the sensor, so at here. But then we're also going to get this amplification of this outside light. And this delta plays an impact in all of this. Some of them would exist there without the delta, but this delta is causing it to be a bit more present. And in lensless imaging, because it's such a complicated mixing, remember if you think of all those patterns of holes, we're actually going to have, congrats, you did it. We're going to have a quite large delta here than with a normal lens. Because a normal lens will also do approximations, but that delta is not going to be as big. So these things don't affect us as much. Those artifacts or noise will be there, but it's going to be there more for lensless cameras. Yeah, you did it. Congrats. I love Will Ferrell and Elf, so I had to put in there. So a simple fix. Okay, if we come back to our setup, so I mentioned, okay, there's some external light here. A really simple fix that we could do is, okay, we had this measurement which got messed up because of the light, right? So what we can do is, let's say if we're able to, we may not be always able to, but let's say we're able to, let's say we can estimate or get a measurement of this light without the leaves on the table. So we're going to measure that. So this is without the leaves. And what we can do is we can essentially subtract it out from our raw measurement. So in computer vision, you could call this background subtraction. So that's one easy fix you could do if you're able to estimate this unwanted light. And then you can get to a more discernible image, as you see here. We don't have this dominating light that came from that external source. So that's one simple fix you could do. And so another contribution we made is, so I mentioned this approach that we had, so a modular approach to kind of address these different sources of noise. So this camera inversion, so inverting this H, as I showed before, we can think of it as one block in our pipeline. But then we could add actually other blocks to our pipeline to address different types of noise. So let me just show them all at once. So we can add a preprocessor. So you can think of that background subtraction as a form of preprocessing. We're dealing with our measurement before trying to do the inversion. So that's what this is. So that was one of our main contributions with some other things more than just the background subtraction. We can actually try to correct. So this is, I threw in this word PSF now, all of a sudden. PSF is another term you could say for the H. So as I mentioned, this H could be wrong. We could try to do some denoising of this H before doing the inversion. And then maybe there's some error that still doesn't get addressed. Then we can have this post-processing. So something after that inversion to clean up. So for example, here you see an image of an approach that would have just had that middle block. If we add the rest of them, we can really improve the quality and the sharpness of that image. One caveat which I can deal with in questions is there is machine learning involved in here, but we can dig deeper into those details if someone has the questions. So since there is machine learning with it, we have to collect some data to try to learn how to address these different types of noise. So in a very scientific way, we set up lights all over the room. And we tried to measure pictures on a screen, so the reason we use a screen here is so we can change the pictures really programmatically. Instead of trying to manually take pictures of many people, I'm just going to use a screen to just display many pictures so I can collect a bunch of data for this type of problem. But we had to manually move these light sources to make sure we have different, positioning of sources. But then also there is outdoor lighting that comes naturally from the outside. But we just wanted to make sure, okay, we don't, let's say, work super well for one particular lighting. So this is what we would call overfitting in the machine learning context. So we wanted to make sure we have enough varied lighting when we collect this data to train the system so that make it learn those different modules, but then also to test it. So just to show some results, I'll just point out two things essentially. So in red are the previous approaches that wouldn't have used this preprocessing. So we can see this blurring of the details in this smaller box or this discoloration. And then our approach with the pre and post gets much sharper quality pictures and a better, it maintains the colors, the original colors a lot better because we can deal with these different noise sources more efficiently. So also, we don't want to just show that, okay, it works by taking pictures of a screen. I mean, not all of us are 2D. So we put some 3D objects in front of it as well to see, okay, how can it generalize to that, even though it didn't see these 3D objects during its training. So that was on the improving the reliability, performance, or we call robustness of these systems. That was one work that we had. So mainly from that work on the ICAS paper. But one thing I was really interested to investigate with these type of cameras is, okay, what can we do with these cameras that normal cameras can't do? Because if we're just going to be mimicking normal cameras, like we were showing before, okay, what's the benefit in that? Now we have this extra algorithm even that we're throwing in it. So what we wanted to focus on in the second part, so what I'm going to present you here, is the security applications that they can enable to complement already encryption that we have from digital standards. So one term that people use for these lensless cameras is that they're visually private. So if we look at these pictures, you wouldn't be able to tell what's in this picture. It's completely blurred out. So what people like to say is that, okay, these lensless cameras there's a notion of visual privacy. But the thing is, all this privacy breaks down if this pattern on the mask is known by everyone else. You can think of it as the password. Sure, I can encrypt or have a password around something, but if my password is out there in the open, or if anyone can determine it, it's not really a private or secure system anymore. So how can we use or build lensless cameras in a way that they can actually be used for secure images? Or how can we prevent such leaks? So because what I showed for you at the moment is that we assume that this correct mask was being used so that we can get an image. Let's say if I flipped the image and I flipped the mask, then we would also expect that, okay, the image gets flipped, right? Let's say I only flipped the mask. So what happens now is actually this whole reconstruction is quite sensitive to not having the right mask, that actually get some completely garbled up image. So this is some intuition. Okay, different masks can lead to bad outputs. So you can think of it as each person has their own separate password. Okay, and essentially we're again playing around this delta, which I mentioned before. Now we're purposely making it larger maybe, or making it harder for someone to get to a smaller delta. So if we come back to our box example, you can think of it as different configuration of holes in that box that we saw. So we had one camera which had one set of holes. Let's say for me, Martin would have another set of configuration, my parents have another, and we wouldn't share that configuration of holes with each other. That would be our secret to decoding those pictures. And the way we built such a camera, so it's actually downstairs if you want to see it later on, and we're still collecting some data with it, is we used an LCD screen. So a lot of the cameras the cameras I showed, for example, this one, I'll show it again for Zoom since you didn't see it. So this is what we would call a fixed mask. So it could just be some height varying surface, or it can be holes as we saw, but those are fixed things. So that means if it leaks and the camera is, let's say, out here on my camera or on my laptop or out there, it gets kind of annoying to kind of go there, unpack the camera, put a new mask. So what we wanted to do was build a camera that's more reconfigurable, that we can reprogram. So we use an LCD screen, so similar to the one on your phone. We use a smaller version of that in front of the sensor. So here's the sensor, an LCD screen, and then still trying to keep it to a low cost. And then these are the example patterns that you would get. They kind of look, if you look at them quickly, you wouldn't see any difference, but actually, as we saw before, just changing it slightly will lead to really bad outputs if you don't have the right mask. So the encryption pipeline will look something like this. We have this secret key, this password. When we take a picture, we're physically using that password to get that picture. So this blurred image that we saw. And then in order to decode that, we actually need to have the good mask. So this is what happens if we have the correct mask, or if we use this more machine learning approach, better quality. And if we have a wrong mask, as we saw before, it leads to a bad image. So this is the feature we want to exploit to build these secure cameras, by varying this mask. So then the question is, how difficult is it to guess the mask? So for, let's say, a hacker tries to guess all possible combinations, is it easy for them to do that? So let me show you some examples here. So on the left, I'll change it. I just changed 10% of the pixels. So you can see just a slight bit changes. On the right, I'm going to change 50% of the pixels. So a lot more, you can notice changes there. So the question now we're trying to get is, how difficult is it for a hacker, let's say, to make this delta as small as possible? So essentially, how can they get that correct configuration? So we saw here some examples. What does 10% look in difference? So we'll do a visual experiment here, where I'm going to vary the number of correct pixels, and let's see if you can identify what's in the picture. So you're the hacker now, essentially. So you got none of the pixels right. Can you make anything out here? Maybe not. 20%, 30, 40, 50. So you sort of get a bias here, because now when you see it and you look back at the previous, you say, ah, now I see it. 60, but I think I heard some yeahs around 40 or 50, and 100% are the ground truth. So yeah, around here we can start to see, okay, we can start to, if I can get 40% of those pixels, yeah, your system sucks, right? But how hard is it to actually get those 40 pixels correct? So it would be what we would call a search space of 1,600 bits. So our normal encryption uses about 256 bits. So it's exponent, like way. If you remember that plot of the cameras, it's exploding how much more difficult it is to actually try to guess that correctly to get into this space of correct pixels. So that was a result we were happy with on the encryption side of things. But we also wanted to see how can we exploit this, okay, unique mask for authentication. Because we can think in a way that, okay, each of these masks is like leaving its unique, we're leaving our unique fingerprint. Like I have my mask, I said Martin has his, my parents, we're all leaving our unique fingerprint because of our particular camera. So then the task we tried to see here is, okay, can we try to identify that fingerprint? So just to give some example of images. So if I used, let's say, the correct mask, if we plug in all of these quantities, let's say that lensless image, the recovered, and the correct mask, we would want to get a low score. If a bad mask was used, we would want to expect a bad score, essentially. And one way we can make this work better is actually by using a lensless camera alongside a lensed camera. So there's no reason why we have to completely get rid of it, but there's a utility in actually using both. So we can think of two captures where we get our lensless capture, but also the normal one, which we as humans can perceive. And then we can also compute a score off of this. And then one term that we coined for this lensless capture is an analog certificate, because it was produced in an analog way by the camera itself rather than a digital way through some digital manipulations. So just some results on this. So I mentioned you can either use a lensed camera or not use one. So yeah, we saw, I guess, the more information you have in this case, and the better we can get in terms of accuracy to detect if a particular image came from someone. And what could be the interesting application for this? So if we think of our smartphones again, iPhones maybe have more of these. We have all these different types of sensors on our phone. We can imagine maybe putting a distorting camera, could be a lensless one, could be lensless, or anything that just tries to distort it. And it would, again, as we mentioned, capture that lensless image with a lensed image, like a normal camera. And then if you remember, I guess most of you have used this two-factor authentication, this annoying thing that says, okay, you need a 6-digit code each time. You can imagine a new pattern being on your mask at each moment. So in order to timestamp as well as user stamp your image. And then this way, if someone tries to, let's say, tamper with the image in any way, by going back to these scores, we can say, okay, there's something fishy with this picture when we compare back to this analog certificate. So more broadly speaking, it could be a way that you can combat deep fakes or ways people may use AI to doctor images. So that could be one way this camera could be used alongside a conventional camera. So we come to the conclusion of this talk. Hopefully there were some nuggets there that you could understand. Just to remind you on some of the main contributions. So we had this theory part to kind of explain the noise. Okay, what makes these cameras unreliable? We had this modular approach to address these different types of noise to make the cameras more reliable. And then finally, we touched upon the security applications for these cameras. And then one of our efforts with a lot of students, I'll mention them in a bit, we tried to build a nice toolkit for other universities to use it, for students at EPFL to use it. So it's available online. It's called Lensless PyCam. And looking forward, some ways that this technology could be improved to maybe get a little tick maybe on the camera usage. As I mentioned, there's some key limitations on the quality. So we tried to address these, but these could still be improved. This algorithm itself could be expensive to compute. We don't get a free image like when we take a picture. So if we can reduce the time it takes to get to an image, that would be a benefit. Some future directions. So you could actually try to optimize the mask pattern with machine learning. So this is not something we looked into. And then also, as I mentioned, trying to improve the performance. So this is this in the wild imaging, this performance in the real world use case. So with that, I'll do a short thank you. There'll be more later, but definitely to a lot of the students who helped out during the PhD in building this kit, and also to my lab mates, Martin, different professors who hosted and support along the way, and yeah, all the funding that made this work possible through taxpayers' money, as Martin mentioned. So thank you, and I'll take your questions.
Very nice, excellent. So time for questions.
Yes, Salim.
Have an easy one to start with.
Sure.
Why is reproducibility important?
Why is reproducibility important? How can you trust the thing if it's not reproducible? It's another way to think about it. Like if someone claims they got some amazing results, but there's no way that anyone can actually make it happen, would you trust it? I'll leave it with that question. Yeah. And is it a harder one then, or?
I mean, I have.
Okay. Okay. Well, are you happy with that answer? Or? Okay, good, great. There's other reasons too, but that's, I guess, the main one. Trust. Yeah.
That helps as well.
So it's in certain contexts it could. So I made this distinction in speaking about a fixed mask and a programmable mask. So in the fixed one, if the lighting is not changing, it probably won't make much of a difference because you're not getting new information from taking the image of the same thing. But if you can change the mask and get new pictures, you're kind of getting new information, so you can improve the quality. Or if you're changing the lighting, which is actually a trick they use in microscopy, you could get more information to get to a better image. So if you have control on the lighting or the way you collect, then taking more pictures could help. So yeah, essentially, so this LCD screen, which I showed before, can do that in a way. So it's built of many apertures. So I forget the percentage we turned on, but we could turn on a fewer number, or we turn on different amounts or different ones. So that's why you could have different apertures essentially for your. So apertures is another term for holes. Like I showed this different configuration of holes with a programmable mask. We can then change this configuration of holes or apertures. Oh, Salal, yeah.
About the authentication bit of like what if you could prove that you took a picture, but in order to prove that you were the one who took the picture, do you have to reveal your mask at the same time? Is it more like symmetric?
Yeah, so you do need to, in order to compute that score, if you want to, let's say, have someone else compute that score, because if you just compute the score yourself, no one would trust it. You need to, where was the authentication slide? I'll go to that. So I think this was a good one. So, or I'll start with this one. So you would need this, what I call the analog certificate. So the raw lensless picture. So maybe I'll give some more intuition. So you need to reveal the mask, because the idea is that you can reconstruct the picture to then show that, okay, it looks similar to the one that I claim is a picture.
One picture in mask, can I use that mask to fake a picture?
You could then afterwards, or it depends who you give it to. Like, yeah, if you trust the person you're giving to compute that score, then yes. But yeah, if you have to end up straight, it could be a weaker security. If you have to reveal that mask to everyone, then anyone can then reproduce it or replicate such pictures. But then that was the other idea of, okay, this mask is also just tied to a timestamp or a user if it's a programmable mask, because there's just so many combination of masks that can cover a lot of use cases or possibilities. I think just behind Solal, yeah.
I find it really fascinating to see that the mask opens so many new opportunities in the sense that there's so many holes, basically, so many apertures, as you said. So
that's true, yeah.
light wavelengths. Have you thought about uses in about security as well? For example, in crop production, where crops can be under pressure of disease or drought. I mean, getting different. I mean, that you can sense basically with remote sensing kind of.
Yeah, so I mean, what cameras already do, so you can turn any camera, let's say, into a lensless camera by then replacing the lens, or you can turn it into a distorting camera by adding that mask. Around that particular application, I guess the difficulty would still be, okay, the ambient lighting, let's say the deployment of that camera. But there are what they call hyperspectral lensless cameras. So what you can do is you use some sort of spectral filter if you want to measure different wavelengths with a lensless camera. So that's possible to maybe build a type of camera that you're thinking about. So if you look up hyper or spectral diffuser cam, I think there's a work on that, on collecting multiple wavelengths, which could be useful for that application. There's one, yeah, Martin.
maybe I'm misunderstood there, but how, I think you implied that it can help identify deep fakes, but how?
Okay. Oh, I heard myself twice. So the idea there is similar to what Solal was mentioning. So we need these two pieces of information to reproduce an image. And the idea is that, okay, if someone is giving me a picture which was deep faked, I would ask them for this analog certificate and the mask that produced it. So I would try to reproduce an image. And then if I see a mismatch between that true image, because this one is harder to fake, and the digital one that they're saying is real, if you see a high error between those two, then you can say, oh, there's probably been some tampering in this picture. So that's the deep fake application of it. Yeah. Simple.
There are questions online.
Sure. My speaker.
Hello.
Hey.
Can you hear me, Eric?
Maybe it's from here.
Can you hear?
I hear you on my laptop now. Yeah.
Okay, cool, great. Hi, Eric. Very nice presentation. Thanks a lot. I had two questions. One is more like about the first part of your talk where you discuss this model mismatch. And the second one is about open sourcing hardware. So we'll start with the first one. So in this first part of your talk, you essentially said that when you have an external source of light, you can consider it as being a sort of noise on your model mismatch. But isn't it actually part of the scene? Like it's additive. So isn't it just like a part of the scene that you're not properly accounting for because you have a limited scope in your imaging algorithm? And if you were to extend this scope to the full field of view, you would be able to make sense of this information, but then maybe the dynamic range would be the issue.
No, you're right. I probably then didn't explain it right, but that's what I was trying to say. That
Okay.
let me just go to that slide then where was it? It's covered by ELF. Okay. So, but as you said, so this noise, this unwanted light, I'm coupling it into the noise term. So essentially, as you're saying, it's this external sources that are going through my forward model. And so it's not model mismatch. The model mismatch is actually coming from, so I'll use some terms here with Mathieu, is we're assuming shift variance, for example, for this H. So it's doesn't have that stoplet structure anymore, for example. So that could be a type of delta that we're adding to it. But I'm not assuming that this external noise is what's in this delta here. Rather, I'm grouping it into the noise term. So that's why, like, for example, as you were mentioning, the dynamic range is an issue here. That's why we get this drowning source from the lamp. And we can't see the actual scene. But by subtracting it out before recovery, that's actually how we can get to that viewable image, but with a lower dynamic range. Because if we wanted to make sure we didn't saturate when we're doing the first measurements, that means we're also measuring at lower max values for the scene of interest.
Understood. Sorry, it's me who misunderstood. It seems like now it's much clearer.
Okay.
Related to that, I see that some of the colors of your images are a bit funny looking. And I remember from discussion we had together that it was because of the white balance. Like it's very hard for this type of camera to calibrate that. Did you find a way to do that in the end? Do you have any, heuristic to balance the white so that the colors would look more natural?
Yeah, so let me explain white balancing then. So white balance, what cameras do now, because as Mathieu was mentioning, the coloring is not as great sometimes. And the reason is because we're not using an automatic white balance algorithm. So that type of algorithm does that, it'll take a picture and it'll try to see where's white in the image. And then it will rebalance the colors of that image dynamically. So on the fly or at that moment when you take the picture. And when we take our data set, we're turning it off because that algorithm is not going to work now. If you recall, everything's getting mixed up. So just because it detects white in one part doesn't mean that it's actually white, because it's a mix of many things. So when we take our data set, now we're disabling it. And what we try to do best, so now to answer Matthew's question, to balance it is that, okay, so there's 3 gains you need to determine, or 2 gains. Because what a camera is going to measure is red, green, and blue. Actually, what we typically do is we keep green fixed and we try to balance red and blue. So what we're doing when we collect our data set is we with known white image, we measure what are the best blue and red and then we keep those values fixed for the whole data set. So we don't do anything dynamic. We just do that simple trick for now.
Understood.
But that is an algorithm which, okay, as they get deployed, we want to be able to dynamically balance red and blue according to green. And that's, I guess, something that could be done when you do the reconstruction, perhaps, to then balance those colors as you would do in a normal picture. So, but it's not a problem we try to address for this work, yeah.
Understood. Thanks a lot. And the last question, very short, is about outsourcing, I mean, open sourcing hardware. I think this is one of the very, very impressive contribution of the work. Like you go all the way down to releasing the hardware you've done and giving instruction on how to build it and reproduce what you've done from the hardware perspective. And I wanted to know if there were any standards, because we know how to open source software. The field has become very mature in terms of good practices when it comes to sharing software, but it seems to me like hardware is a bit wilder to share efficiently. So what are the lessons learned from your perspective in terms of how to efficiently share such artifacts of research?
Okay, first, I agree with you. It's hard. Lessons is this is where, as I mentioned before, where I had a help from a lot of students, and I think working with people is important here, because if someone else is not going to understand it, then you probably didn't make it in a reproducible way enough. So there was a lot of iterations with students or with other labs trying to share designs. So for certain aspects, there's good standards, like for 3D printing, for, let's say, tutorials with Raspberry Pis or Arduinos. And let's say our approach here was try to use accessible components, because then there's more of a community around it, because this is the type of thing where you need a community drive behind it. Even for software, there has to be something that's easy for the community to use and something that they want to use. So it's a lot of iteration. I would say probably iterating quickly, just trying to put out prototypes, and then getting motivated students to work on it with you to then see, okay, what didn't make sense, because most of the time I made bad decisions. So then it was good to have that feedback from the people. So being quick in receiving feedback, which I think is the same for software too. So I would say being quick iterations, but then also using low-cost accessible stuff. Because let's say a lot of what people were using in the Lensless community before were very high-end sensors, very specific optical components. And this is harder for someone to know where to buy it, how to buy it, or to even put in the money for it. So yeah, I would say trying to prioritize accessibility.
Thanks a lot, Eric.
Yeah, thanks, Mathieu. Julien?
So that we can put an image using the mask, and that's without the mask, it's very hard to cover the original image. But as humans, certainly we can distinguish and evaluate if an image looks real or looks blurred.
Yeah.
So maybe there's a way to quantify this likeliness that the image is correct. In which case, could it be possible to try to guess the mask iteratively by trying to optimize this quantization?
Yeah. So to have some sort of a loss where you get some feedback, try to go back to improve it in a quantitative way. So that would be a very cool hack. It's not one that we looked into, but it is one that is of interest. So if I can try to rephrase. So what he's saying is that instead of just trying to randomly guess, which is kind of what I was showing before, like, okay, with the 0, 10, 20, let's say you randomly guess 10. Now we can try to compute a score, like the similar scores that I had, and then try to improve our model. So we would still need to figure out a model to I guess, learn, because we need some model how to predict mask functions still. So it would be an interesting hack to try, but I don't know how successful it would be, or if someone's heard of a similar tried hack in digital encryption, because I guess here there's a bit more structure in the image, so it's a bit, there is some, let's say, physical information you could use, but I don't have a good answer besides that. It's a good question. Yeah, Andrew?
Kind of related. Thinking like, especially if you have the opportunity to, you don't know the mask, but you have the opportunity to look at multiple real image, masked image pairs. Like,
yeah.
Could you think about could you guess the mask by, then you're basically optimizing over, right, this forward model, with some parameters, which are the mask.
Yeah.
But I mean, that's going to be, it should be linear in the mask in some way. So it seems like maybe a potential attack could be get a bunch of images and just optimize over the mask to.
So I have a variant of that, a simpler thing than trying to guess, let's say, physically determine the mask, which was this, like collect a bunch of images. And let's say that the dummy idea is, okay, let's just try to train a neural network to learn that mapping from lensless image to lensed image. So let me show that result. Yeah, here we go. Okay. So what we did was something similar to what you said. We collected about 20,000 images, which is standard in this domain of images from a single mask. And here I didn't use any PSF for reconstruction, so I'm just using pairs of lensless images and lensed images. And here you could start to recognize some of the content, right? So that's one hack that someone could do if you have a fixed mask system. So what I was mentioning before, which was a limitation of such systems. And this is a comparison to, okay, when we have the full mask information. So the idea is, okay, actually when we're using the system, whenever we're taking a picture, we're changing the mask pattern. And if you tried to collect a similar data set as this, actually the data, you could get the colors of it somehow, but the content of it is really harder to capture. And the reason behind here is because it's not anymore a linear model for your camera system, because now each image has a different forward model, right? So you need to learn a dynamic forward system, but the only information you have is that input image or that measurement you made. So one of the arguments we made for this program mask system is that, okay, it becomes really nonlinear in a higher search space to then determine that mask for such a, let's say, I think the term for this would be chosen plain text attacks, where you have a set of attacks that you've made, for example, and you know the outputs, or maybe known plain text attack, one of the two, and then you can try to, let's say in this case, try to train a neural network to learn that mapping. And here's just kind of the strength of using that variable mask. It's harder to learn.
I guess the security or authentication would mainly work if you have like one mask per image as opposed to one mask.
Yeah, I mean, that would be ideal case, but you could also, maybe you still have 10 masks, 10 images from a particular mask, but yeah, you want to have a variable mask. That's the key part of it. I think Stepan first here. Oh, one more question on that. Okay, let me just do, or I'll do Lebo and then I'll try to look for the online one. Okay.
Hey,
oh, sorry, the person in the room is going, and then you can go online.
Sure, thank you.
All right, yeah, sorry.
Question about the masks. You talked a lot about the noise from external lights.
Yeah.
The masks themselves, as far as I could see, maybe you could describe that they're like kind of rectangular shapes or like holes. And if you fabricate them with 3D printing, maybe you have some curvatures, or so the diffraction is not as nice as if you have something micro-fabricated. Do you think some of the blurriness might come from this, or is it really more from the external light? So
that type of blurring would affect more the, let me go back to the equations then. I won't fall for him again. So Lebo was asking, actually, there was a few layers there. Let me go one at a time. So you were asking about you mentioned about the fabrication of the mask, because there's different ways you can fabricate the mask. You mentioned 3D printing, which may not be as precise as if you were to use the similar type of technology as manufacturing chips, where you could be super precise. And there you could have finer structures, which could help you get sharper images. So there's multiple types of masks we considered. One of them was the LCD screen that I showed, which has a limited resolution because of the shape of the layout of the pixels. We used even simple Scotch tape, which has very micro features. So that was one way they keep low costs, which was an idea from a lab in Berkeley. We had a lab from Korea who fabricated with UV lithography this mask here, which you can also then see. But it's what you're pointing at with the size of the structures. It's true that, okay, with a 3D printed mask, so we have a comparison with that in Thesis, it leads to you more blurrier reconstructions, because you can think of it, the sharper features you have in your mask, the higher frequency information you can detect from your image. So it's not really a noise that I would say that comes up, but rather a limitation of your imaging system now, because let's say the blur of your system is too large now from too large of structures. But what could pop up as noise is actually because another reason why this is an estimate is because we don't have the ground truth, like the perfect knowledge of this. The way we try to get it is by measuring it through a calibration. So then that could be a situation, like as you're saying, maybe we don't capture it super well. We don't estimate it super well in our calibration process. I don't know if that answered parts of it, or was there a part that I missed out?
Is there a limit if it's not perfectly sharp, I guess? Because I guess you have a design in the computer with perfectly sharp shapes, and
Yeah.
when you're doing the transforms, I mean, maybe if you estimate the curvature, you have an upper limit of the deep blurring or the sharpness.
Yeah, so I mean, in that case, we always calibrate, we measure the PSF. So even though, okay, always in the 3D printed, but in the programmable mask, that's true. Actually, there we simulate it. And there, yeah, we're introducing noise because we're not getting the perfect shape of those individual pixels. But there there was some modeling that we added to it. Let me just show a few examples of them. There were just some more global things that we tried to do. Like we tried to account for diffraction, as you mentioned, by taking into account the knowledge of how big they should be. There's this concept known as dead space between the pixels. So it's these black areas between pixels that we can't actually control. Previous work most of them would just have blocks that are just concatenated. So there's different steps we try to improve let's say the realisticness, I'll say that for now, of the simulated PSF. But yeah, when you simulate PSFs, that could definitely be an issue then, that you don't perfectly get a sharpness when you fabricate it, or you're not modeling it well enough in your simulated PSF. Yeah, thanks for your question. Yeah, there's an online question we can get to now.
Hey, Eric, this is Dandeep from UMBC.
Hi.
So, congratulations. The presentation was really good. So I just want to ask, did you consider applications for AI inference or training? Because lensless makes it, I'm assuming it makes it faster than a lensed camera, right? You get images quicker. So the inference speed or the FPS that you get by the lensless camera, I'm assuming would be higher.
Yeah.
So did you,
So I can repeat the question.
Sure.
So I'll repeat the question. Let me know if I misunderstood.
Sure.
But I guess what he was saying was that actually we can use the camera as part of what's called the AI inference process. So let me go back to this image application of the car example. So in this car example, it's going to be using a conventional camera. It's going to do a bunch of computation and then to try to make a decision if someone was there. And what I think Dandeep was trying to ask is, can the lensless system do part of this computation at inference? Is that your?
That's right.
Okay,
That's
so
right.
that was this question. And that's definitely the case because actually we can try to, so this is one of the early works we did in the PhD. I didn't present it here, where so we have this programmable mask, for example, where we can change the pixel values. Let's say we determined a configuration that works really well for classification. So we could try to train, let's say, the classification with that first layer of mapping, because essentially we're doing if I go back to this image, we're doing this mixing of information from the world. So maybe there's a way we can mix that information so that it's useful for the camera to then make its decision. And then actually what we were looking in that work is actually we don't need to collect full resolution images. Like we could do classification on, this was in simulation, caveat, but you could do classification on 12 pixels of captured content. Or maybe it would have to be 100 or 200 in real life, as opposed to a megapixel, which is 1 million pixels. So you could use that mixing of information and learn that to work with smaller pixels to, as you were pointing, hopefully have faster inference because now you're working with less data, or you did some of the inference computation beforehand. So we looked into it to answer your question, but only on the simulation, because actually training this is difficult because getting a realistic model of a lensless camera is still an open problem. And thankfully it is, because if it was easy to replicate lensless pictures, the authentication stuff would break down. And the security stuff would break down. But it's actually very difficult to perfectly model this system.
So do we even need reconstruction at this point of time? Because if I have just the information from the mask, I could train the models on the lensless capture itself, rather than then I don't need reconstruction, right?
Yeah,
Have you ever
yeah,
thought of
exactly.
that?
Yeah. So that was actually tying back to the question I mentioned before, do computers need human eyes? And the only reason we're reconstructing images is so that we can understand if the system is working better. But you're absolutely right. We can work directly with this, let's say,
Lensless capture.
lensless image. And that's what we were doing in that work. And then there's been other works that have also worked directly with this to try to do pose estimation, that try to do classification on it. Those have been the main two tasks. Usually it has to be more global tasks, but because of this blurring, it's hard to really do, let's say, super resolution or detect super fine features in the image.
Mhm.
Yeah, you could definitely just work, a computer could directly work with it, which is one of the motivations I mentioned before.
All right, that's great, Eric. Thank you.
Thank you, Dandeep. Was there another question from the audience? Otherwise, I'll go to, I think maybe Gloria. I'll go to Gloria first. Yeah. 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 So we're not modulating fast enough for the purpose of our data sets. We were just trying to get images of different masks. So, but otherwise you'd be limited by the frame rate of that LCD screen, which I think would be about 60 Hertz. If you have a higher end electronics, you could probably modulate it much quicker. What was the other part of the question? Or the so yeah, the approach, let me go to the prototype image then. So everything is being controlled by Raspberry Pi in the spirit of keeping it low cost. So there's an LCD screen that's wired here in front of it. And then that same Raspberry Pi is controlling a sensor. So essentially when we want to take a picture, we set the pattern on the LCD screen and we take that picture and we store with that picture the pattern that we programmed on that mask. So that later on we can simulate the PSF to do the reconstruction. For which one? No. Well, because this one we can't reprogram it. So here we've as I mentioned to Lebo, we measure it before the pattern or the PSF, and we're only going to use that PSF when we do reconstruction. So it's a one-time calibration. Whereas here actually we don't need it. We could actually try to measure the PSF each time, but that wouldn't be practical. But here, since we know the structure that we programmed on it, we're storing that the pattern, and then we simulate the PSF when we want to get back to an image. So yeah, the process is just set the pattern, take a picture, and store that with that picture, the pattern, so that if we come to the authentication example, that's sort of the secret key that you need, that was used when encoding the image, but then which you could then use to decode the image at a later date. So you can think of it like already when we take pictures with our phone, there's all sorts of metadata that is stored with it. So there's dates, maybe the lens or the camera type. You can imagine, okay, here we're now storing the pattern that was taken with that picture. So
yeah, maybe I'm just what's the advantage of using this over a reproducible meta surface, which is just changing the space?
I guess cost, but I'm not so familiar with meta surface, and I'm in. It's true that okay, there you getting to Lebos, then you can have much more control, right, at a smaller scale. But at least to our knowledge, and on let's say Raspberry Pi stores, there wasn't any reconfigurable meta surfaces that we could buy. But that would, I mean, that's definitely a cool thing to then work like close. I mean, at EPFL, we have all these researchers that are working on these things. And if you had come earlier, we could have worked on this. Thank you. Fun, yeah.
Well, I'm thinking, why not simply using hash function to check if this fingerprint already is in your database or not?
So a digital hash, sure. So I mean, the goal here was to have something that could complement digital, let's say, encryption or digital techniques. But what we wanted to do was use something really in the analog world, which is putting, I mean, we found this term cute, this analog fingerprint on the image. And okay, I lost my train of thoughts. Can you repeat your question again? Sorry.
So my question is, why not just hash or creating that and see if this hash value is it in your database or not?
So if the hashed value, so you mean if the altered image is in your data set? So let me go to the image because it's not super, I glossed over it. So the idea is, okay, let's say you gave me a picture of me with bunny ears, right? Let's say that's the altered image, all right? And then the way I would check to see if this was deepfaked, okay, you could use common sense maybe, but let's say no, we want to check it. Is that, Fan, I'm going to ask you, you claim that you took this picture with me bunny ears, right? That's your claim. So what I ask you is, okay, give me the lensless picture. So the thing is, I don't have the bunny ears one in my database, so I can't compare to that. But the comparison I'm going to do is I'm going to say, give me the lensless equivalent of me with bunny ears. And as I was mentioning before, if you can simulate lensless systems, then you could break that test. But we're assuming here you can't simulate a good lensless system. So you would give me this picture, and then you would also then give me the mask that was used to produce that picture. So giving those two, I would try to recover a picture of me with bunny ears. But then if I see that picture doesn't have bunny ears, then we're like, hey, Fun, I think you added bunny ears to that picture. So that's kind of an explanation of the type of test. We didn't do that. We didn't go deeper into the deepfake, but it was more, we in this work, it was more establishing, okay, the scores we can compute with authentication and how we can do encryption in analog. But hopefully that example gives you an idea of it. But there's that, we wouldn't have that, tampered image in a database to compare with. So yeah. Yeah, thank you. Pinner?
You can also test with 3D objects. Have you ever done a test where the surface is a bit reflective, and if you did, how did that affect the covering of it?
So I haven't done 3D. We had a student, Julien, who was looking into 3D actually, but that was just more to try to reproduce that, but not in terms of the research side. In terms of reflective, that is a trickier problem because but it's not that type, that would be a different type of, let's say, illumination. You could think of it as maybe another type of illumination that's distorting the scene we want to, because maybe now this point is over dominating the rest of the points, but it's not a type of challenge that we looked into. Yeah. Andrew, yeah, then Mihailo.
Maybe I was confused, but so my understanding was the hard part. The hard thing is to guess the mask.
Yeah.
And you were saying we know the mask on this slide, but the hard thing is just to simulate system. Right?
So both are hard. Yeah.
If you have the mask, I mean,
yeah.
I agree. You're trying to do both at the same time. That's another. Mask.
Yeah, that would be like a blind deconvolution problem.
Yeah. But if you know the mask, why is it hard to see?
If you know the mask, yeah, then the system is compromised. But then the idea is, if our lensless cameras were always just fixed masks, then once knowledge of that mask leaks, then it's done.
I'm just trying to understand what you put on this slide.
So this is for authentication, not for encryption. This is just the score you could compute with the correct mask. You would use a lensed image and a reproduced image and compare them to see if there's any difference between those images. Yeah. Wow, you guys have great questions. Understood it well. I'll go with Mihailo first.
So I think the first part of the presentation you mentioned the results with physical mask and blood loss.
In the first in the introduction, or yeah, the modular approach. Yeah. This one? Or?
Just one question. So let's say you have a mask and then you schematic that, and then you put your machine learning alchemy on it. And now I try to use your algorithm with the mask that I'm 3D printing. So is it going to work well? Or
so this was another theme in the thesis, which
I'm just focusing on the robust and reproducible part of the thesis.
So this was actually, this is the term that I used in the title called generalizable. So Mihailo is kind of pointing to that. And I don't mean generalizable necessarily. I used it a bit differently actually, or more broadly than the machine learning context. Because what Mihailo is asking, does it generalize now, not just to say different types of images or different contexts, but now a completely new mask? Is that it? Like, yeah. Yeah.
Let's say I want to take photos, pictures with the mask, and your algorithm that has been trained with your mask. So is it going to work well, or I have to retrain with my?
Okay, so then there's multiple parts. It depends. So it's a simpler problem than what I was going to state. Then it's like you're trying to do something similar to mine, but there's some manufacturing differences. Is that it? Okay. So it depends how large those manufacturing differences could be. So I didn't do this work, but it was the work from this group where they fabricated many of these similar types of masks, and they wanted to see how robust it is to those tolerances. So that's more a study you would do on, let's say, your manufacturing approach. And in their approach, it worked well. They were able to take the model trained on one mask and then do it on another mask, and it worked fine. Since we didn't focus so much on manufacturing, but rather low-cost things, we didn't do that sort of study, but we did another one similar to that where actually, let's see if I find it here. It's gonna be really in bit. So these are more of the private different slides. Okay. I show it from here. Is it? Okay, no, it's I'll just do it from this image. So since we had to sort of solve a problem similar to what you said, because when we vary the LCD screen, we're essentially changing the mask that it may have been trained on, right? So our approach to deal with it was actually that when we collected our data sets, as I was mentioning earlier, we would change the mask, but then to make sure we weren't overfitting to those set of masks, we would test on a set with a different pair of masks. So on that case, we're trying to see how well we could get generalizable components so that you can then swap out different LCD patterns. So this multi-mask training is one way you could improve then the robustness, as you were saying. Like if you manufactured a few and then just to make sure that they could generalize across those so that if you manufacture a new one, that would be one way. So yeah, you would have to do the machine learning if you wanted to be sure. The alchemy, yeah.
Another question. So that includes the LCD masks. And question, a follow-up would be, you can change your mask and then you apply the set of images, and there was a question before, make it more robust by having several acquisitions with different LCD masks.
Yeah, so actually maybe this one is a good example of comparing different types of masks. I didn't show this before, but yeah, so here I was using what would be called phase masks. So they have more of those micro variations that we were talking about before. And we get those higher frequency details because we have these finer structures. And the images we would get from LCD based, which we call digicam, they're much more blurrier. So we have images from them. And as was said before, since the way we could improve the quality is by collecting more images, but then that would lengthen, let's say, the acquisition time, but then also the amount of data you need to use for imaging. But it's definitely something that could be done to improve the quality so it's closer towards these better types of masks. Okay. Sakib?
So starting with the same, I have a question, like, are there type of masks that are better for different lighting conditions or something, like in the image, like, I mean, that you're trying to reproduce?
Yeah.
And secondly, I have the same question as someone asked before. Why is it so difficult if you're given a mask, like fixed one, that you train a model that can replicate the image from a lens camera? Like, I mean, I think it should be able to do it, right?
Yeah. So let me do the first question. So mask types. So the intuitive example I gave was the holes, right? So that's what we would call an amplitude mask. We're just letting light in or letting it go through. So that's, I think I have a good table in these slides for it. No, I don't. Okay. Oh yeah, here, sorry. So these are different mask types that you could have. So the one with different holes, let's say what we call amplitude, would fall in this top row. And what's good about those is that they could be easier to fabricate, they're more accessible, they're lower cost. But then what happens is you're actually blocking lights, so those are generally not the best masks to use. If you can use a phase mask, so this is a mask that lets everything through, and what's different there is that the surface of it is varying, because we need some way that light kind of arrives in a unique way at each pixel. If we had nothing in front of the sensor, every pixel would kind of get the same information. So the goal of the mask, so in the lens case, is okay, we're going to focus one point in the scene to one point, but with the phase, we need some sort of variation. So in general, the phase are better. So you have lower, let's say, acquisition time. So hopefully that answers on the mask type. And usually fixed gives better quality because you can design really micro features to get those higher frequency details in the image. Because programmable, as we saw with the prototype we have, it's going to be limited in its resolution of the actual mask itself. So that's like on the mask types. And then on, what was the second question? Was on
Given a fixed mask.
a fixed mask, yeah.
Why is it so difficult in terms of quality like that you cannot match something from the lens camera?
So those were the results that we've been showing.
Because in my opinion, you said 20,000 images, right?
Yeah.
You train the data set on. I think if you just increase it to maybe, like, I don't know, 1 million.
Yeah.
It will work very good.
It probably could. But collecting the data set is not trivial. So yeah, there's a scale thing that still needs to be explored. So, but then I guess the reason we didn't want to push further than that is because now we're still only going to replicate a lens camera, and that wasn't really our goal of trying to have a new application or a new use case. So you could probably get it better, but then what? Why don't you just use the lens?
I thought in the beginning you said it's low cost and there are benefits of lensless camera.
If we use it as an alternative, but the reason why we have this explosion of lenses is because they have reached that low cost usage and that reliability, but lens don't. So we still need to explore in this space where we can't collect 1 million images per mask, because that won't be, if that's the solution, then it's not a very scalable solution. So but if it becomes easier to collect it, or if it becomes easier then to simulate realistic, because when people try to simulate on, let's say, 1 million images, when they try to train it on real, it doesn't do as well. But what you could do as a trick then is just collect a small amount of real data and then fine tune on that so that it can learn maybe those special artifacts. So maybe that could be one approach where, let's say, you have a rough idea of that fixed mask, you train on 1 million, as you were saying, and then you collect that 20K to fine tune. It could probably do much better, yeah. Yeah, thanks. This is the private defense. Are there any more questions online though? Okay, any questions? Or you can ask me afterwards.
Some guy wants the upload. Was very interesting. Yes, it's all done. Congratulations.
Thank you, Martin.
I guess you get
Maybe put a nicer slide on the back, maybe.
Yay. So with this, I'm happy to give you a host.
Oh.
Which side you want me to be? Dr. S. Science from EPFL for your thesis, brilliantly defended in private and in public. So maybe somebody want Yeah, in the tradition, the advisor says a few words. Let me start by saying that the advisor didn't do very much. If you know Eric, he doesn't need an advisor. Anyway, the other thing is that is a challenge with Eric is it's very hard to speak after Eric. As you can see in the picture here, he's a very public person. I think that's at Lausac. The picture is from Lausac. And I remember once having to speak at Lausac after him, and it was not an easy experience, right? Because he's such a natural speaker that, I felt very little in that context at Lausac. But anyway, I'm going to say a few words anyway. So usually we try to go back to how Eric, came to the lab. And as you know, he has a very interdisciplinary background, let's say, or intercultural background from Italy, from India and from the US. He grew up in Silicon Valley, I believe. A nice picture of the Golden Gate. And he has also a very interesting and unusual curriculum. He did college preparatory, which is a Jesuit school, I read. Okay. Now, so for just if you don't know the history in Switzerland, Jesuit schools were forbidden for a long time, actually, because of religious warfare or something. But of course, the Jesuit school are very famous for their outstanding education. Then you went to the United World College, which is also something very original, right? I mean, this looks a little bit like Harry Potter on steroids or something. That's a campus in New Mexico, okay. And from there, interestingly enough, he goes to this place which I used to know as Jacobs University in Germany. And I think it was still called Jacobs when by now it's called Constructor. I say it has been taken over by an engineer, I presume, to call it a name like this. Now, Jacobs University is one of the very few private universities in continental Europe. And I think this was very original also for your parents to send you abroad into this, very original place in Bremen, where you graduated from, and then came to EPFL. And I remember, but I couldn't get the facts really right. I have the recollection of a Skype interview with you, but I might be wrong because you got a fellowship, right? You got a master's.
So yeah, I think I reached out to you, and then you put me inside of Yuri.
Okay.
And then you invited me here.
Okay, but at first I said Jacobs University, a private university in Connecticut, But this guy, of course, you get to know him, and you immediately get fascinated, right? Now, the other reason he showed up here, and I was trying to get the numbers from Paolo. We're supposedly a quantitative lab, but we don't have the numbers, is that supposedly you knew about LCAF because of our online course.
Yeah.
Okay, so I went through the numbers. So currently there are 100,000 people taking the MOOC, right? So we got one hit with 100,000 people. So now, speaking of good investment of taxpayers' money, anyway, but I'm all happy, right? I mean, one Eric is worth 100,000, no question. Okay, so he came to do his master's on an excellence fellowship from EPFL, and but only when that's a great one. Thank you, Eric, for digging this out. So he was in the local newspaper when he got his degree from Bremen, from Constructor University, as it shall be known from now on. And he says, "Oh, I'm going to do 2 years for a master's, 4 years for a doctorate." Did you add them, or you were going to do both in 4 years? I'm not sure. And I'll go to either Stanford or im Schweizer Lausanne. I think the people in Bremen didn't know about EPFL, right? So they thought you would go to the Olympic Committee or something. So anyway, so Stanford lost our gang. He came to EPFL, and we have been happy ever after. But of course, he's a guy who keeps moving and exploring and so on. So he finishes his MS and immediately goes to explore startups. One, I think, which is in California, DSP Concepts. I think it's in Silicon Valley. Another one, which is in Paris, Snips, which was taken over recently, I think, by another company, actually, by Sonos. Very interesting. And so there he was actually doing audio, right? So everybody was thinking, oh, the guy is going to do a PhD in audio processing, which I guess he's also a great musician, by the way. But no, he goes into lensless images. And there, I really have to say, I like photography and imaging and so on. I spent fortune buying lenses for my cameras. Here is one of them, very beautiful, old, I forget if it's a Leica or something, costs a fortune and so on. And the guy comes to the lab and says, oh, let's get rid of the lenses, right? But okay, we are flexible. Okay, so he started on this topic, which is a very original topic. And one thing I liked with Eric, and you know this, you could also see it from the public presentation, he's a very, very good communicator and very pedagogical researcher. And so I did out, I think, the first report I have from you, which was right when you started. And, you explain, okay, here's a pinhole, here's a lens base, here's, what I'm going to do. And not only did he do it, he supervised a lot of students, summer students, and so on, summer interns, etc. But no, is this, one day, Nicoletta, who of course runs the show here, she's the administrative assistant of the lab, says, oh, you have to sign off on this grant. I said, I never wrote this grant. She said, no, Eric wrote the grant and got the money, right? So, so he was essentially running LCAV inside LCAV. But if you know him, he was also running Lozak, right? So, okay. So I think that was the other experience that really I found amazing, and I saw other people from Lozak here in the room. This is a fantastic initiative, completely student-driven at EPFL. If you try to do this top-down, I mean, we know these people who run places top-down, right? Nothing happens, but the students do it, and something fantastic happens. And you did it for a number of years. And when I was in town, I tried to come to either the competition or the final event, and it was always, I mean, there was so much positive energy in the room. It was really a pleasure to participate. Thank you very much, Eric, and the team at Lozak for running this. Okay, now at EPFL or at LCAV, we also do some fun stuff. We work hard, we play hard. So these are images, I think, from one, that was maybe the first ski day after COVID. COVID was not a fun period, as you can guess, but this was, taking back the party somewhere in the mountains. I forget where it was. And of course, Eric works very hard, but every now and then, even Eric needs to take a nap. Okay, so I think he's on the back from the ski day. Now, of course, Eric, he was very productive, publishing a number of things in different dimensions, in journals, in conferences, and so on. Also on different topics. He published, of course, on his acoustic work, work with Robin, who was mentioned earlier, then things, of course, on lensless imaging. And amazingly enough, he's a guy behind open science, reproducible research, and all this. I managed to convince him to write a patent, okay? And the patent is here. Well, that's the invention disclosure. We'll see what happens to this one, but, we sort of felt, or I felt, it's really nice to invent all these things and then to buy it back from Silicon Valley. Maybe we can actually take a patent, in particular on this deep fake detection, which I think is quite a fundamental issue in current digital technology. Very good. So he defended his thesis. It was mentioned with Sabine, who is now the dean. She's our boss, was the president of the jury and a colleague here, and outside experts. They loved the thesis, of course, as we all did. And now, as I say, for something completely different. I mean, that's the last thing I expected from Eric, is that he would go to private industry, Lozak, open, reproducible, all this. But, he told me, no, Hugging Face is completely different. So I went to the Wikipedia page of Hugging Face. And what do I see? This article contains promotional content. Please help improve it by removing promotional languages. I don't know if you knew this, but okay, the Wikipedia page needs a little bit of tune-up here from Hugging Face. And but with all this, I'm very happy actually that you joined a very interesting AI company, one that is definitely different from many that we hear from. And with this, dear Eric, we wish you all the best for your future. Congratulations again.
Okay, cool. So I hope you can hear me. Well, so as Martin said, yeah, it's always difficult to speak after Eric. Well, it's even more difficult to speak after Eric and Martin. So what we tried to do is that we wanted to make a lensless investigation on Dr. Eric. But unfortunately, this was not super easy because we are not lensless experts. So instead, we will aim at a lens-assisted investigation about Dr. Eric. So to do that, as scientists, we collected data from colleagues and friends, and we tried to uncover the different facets and personality of Eric. And as a scientist, we are pretty happy because we got a lot of data actually. So who is this guy? How does he work? What is his personality? So let's get started. So Eric is a very, very hardworking scientist, and this we've seen it. We see him all the time with a laptop. Well, okay, maybe not super hardworking all the time, especially when he was supposed to work at the lab. But well, still, like the laptop follows him everywhere, everywhere, even at night, even in the train. And what he does is that sharing his passion for science and engineering, he's a very, very good speaker. So we saw him in different events, presenting different stuff and cameras and at LOSAC. Well, sometimes the message may not be super clear, well, everything about technology. Well. But anyway, he's a very, very successful and very talented guy. As we could see, the best student paper at ICASP this year, or best demo at ICCP. But as Martin said, Eric has had like many lives and before doing his PhD actually. So if we take a look at his LinkedIn page, we can see that in addition to a PhD, he was already a scientist, an engineer. He has done investment apparently. Well, and also running, of course, LOSAC, which took probably as much time as pursuing a PhD degree and doing research. So we have many, many pictures of LOSAC and Eric, most of the time pretty happy with LOSAC things. But another thing that and no one has mentioned yet, but Eric, is his secret project, which can be known as well as the Army of Interns. And actually, when we were in the lab, it was very usual to see Eric with many people working for him, following him. So for security reasons, I won't display all the faces of everyone, but there were a lot, like much more than them. And maybe, who knows, one day there will be like Eric Inc. or something. We don't know, but keep the ears open. But anyway, beside this professional aspect, Eric is a very sportive guy. You see, like he of course likes football, and he looks very professional when he plays football. Same thing when he's baseball. I've learned that he went into swimming as well very recently. I don't have any picture, but that would probably look like something like that. Well, there are also other sports where it may look a bit less professional. But well, I mean, not too bad. So with that regard, actually, we have a couple of gifts for you. So of course, we like football. So we have a cap from the Lausanne team, but more than that, we have a nice football T-shirt with your name. I don't know. I actually don't know where the camera. Yeah, it's blurred. Anyway. Well, so of course he's a sportive guy, but he's actually a natural lover. He likes to be outside, and look how confident he is on these very beautiful pictures. So we wanted to offer you a bit of sport gear as well, and outdoor gear, but we know that you're moving out soon, so it may not be the most convenient. So we still have something though. We have a little memory from Switzerland. So this is a Swiss Army knife. And we have a gift card for Ovio Camper, so you will find that in Paris, and you can buy anything you want, and good gear over there. In addition, we know that Eric loves food, and we have a lot of pictures that prove that. So he likes cooking. He's a very, very good cook, actually. So cooking, cookies, grilling, maybe. But he also loves eating, of course, and we have even more pictures of him eating. I guess I won't describe everything, well, but enjoy the pictures. Fondue, very Swiss, and Indian food, I guess. So with respect to eating, we also have a few gifts. So I guess this is very representative of the Swiss. No, maybe not. But we have very specific Swiss supplies from the army. We know that you are also going to Paris, and so this is a special gift from Jonathan, some sort of a welcome gift.
It's expired.
I hope no. Special gift to welcome you in Paris. It's something that only French people do, I would say. It's like pâté de grenouille. But well, we also choose a very nice 7-course dinner in a very fine restaurant in Paris, so that you will enjoy for 2 person with the Accord event, so with the wine. All right. What else? What else? Well, of course, you know, Eric, that he's a very good scientist, but he's also a very cultivated person, and he likes actually good movies. He's an excellent piano player. He plays guitar. He likes traveling. His favorite game is actually the New York Times crosswords, and I'm sorry to hear that probably it's becoming a paid subscription now. But anyway, we know that you read a lot, and you have this list of American books that you want to read. Again, that's not very convenient to carry to Paris. So we've offered you a gift for an American bookstore in Paris. So you have a gift card for that. I don't know if you know this library. Okay, great. Well, and final part, of course, Eric is a very fun and cheerful and social person, and we have a lot. Like, probably the most amount of picture we have is Eric with people. Like, I think he has something for gathering people together. So we have pictures with lab mates, another conference, dinner, parties, a lot of partying again, and more gathering people, birthday, I guess, a lot of one. Again, well, we see he has a lot of friends. He was not alone in Lausanne. So with all of that, great congratulations, Eric. And just before leaving the floor, I have to display this very funny video. So I'm not sure I'm allowed to release the name of the people who released this video, but I let you enjoy. All right. I think this is from nothing of them. They're great having you around.
Okay. So, yeah, it's really amazing to have all you as friends. I was in between quotes. As Adrian said, I like food. And this was a funny quote on thank yous. Taco shells, they made a long journey, but a PhD is also a long journey with a lot of support, and super grateful for that. And as this quote says, I'm just so, like, I have such abundance with you guys, and I need my breath. So yeah, let's try to get through this. So there'll be good food as well too. One thing Martin didn't mention is I also have an Argentinian roots. So there's gonna be some empanadas too, some Indian snacks, and yeah, some American cookies, as you saw. And then there were too many of you, so we also got a caterer as well too. They're great. We had them through Lozak for a few times, so hope you enjoy it. First, I'd like to say thank you to Martin. I mean, he showed a picture from Lozak too, and I mean, he was a guy, I guess Solal or many of the people at the beginning would know. Martin enabled so much for us at Lozak. Like, we were stuck. No one, obviously, when you first start something, no one knows if they can trust you or not. luckily, I was working in the lab with the president. He says, "Oh, by the way, did you hear about this LOSEC project? They asked if they could use the building," and boom, we got a reply, as you can imagine. So things can come from the top, but really, Martin, I mean, besides that, he's such a great mentor. I mean, I think all of us who've been a PhD student with him or maybe interacted with him, I mean, we just know that he just is so interested in the growth of people. It's not about metrics, about pushing or this. He really wants you to grow, be curious, think outside the box. And his support to the whole PhD process, even though he said, okay, a person like Eric, I mean, I couldn't have done it without him. Like the last 10 years I've known him, and he's opened so many doors for me, and I'm really grateful for that. And as you mentioned, I had a really great thesis jury as well too. I was really honored to have Christine and Ashok. I mean, they put out a lot of great work, reproducible work as well too, open source work on lens imaging, which is really a foundation for a lot of what I did. So that was a picture from the private defense. Christina and Ashok couldn't make it. They're based in the US, but yeah, it was a great time. Here's a nicer picture of them, but yeah, super great. I don't know if you're listening, but I'll reach out to you and thank you so much for going through the thesis, all of your positive feedback as well too. And then there's a lab, LCAV, as I mentioned. So I was here 2 stays, once during the masters, as Martin mentioned. So yeah, there's many faces here, which I'll try to remember. And then Marta, who I think I saw walked in, Hanje, Paolo, Mihailo, Karen, Dalia, Gilles in the back, Mathieu, I was also there, Kiki, Miranda, Reza, Gulnush. Yeah, thank you for that time, which was my first entry into research to learn about just the awesome environment and just the lab that Martin could foster here, and I'll mention a few people. So Robin, and as he mentioned, was a huge mentor of mine when I first came. I mean, he pretty much taught me everything around open source and Python, and that's opened so many doors for me. Hanje as well too, who was my supervisor during the masters. And then during the PhD, I mean, I had met Sepan before and Mathieu before. Sepan and Mathieu were a huge help in the beginning when I first got started on this new topic. I mean, I switched topics, but it was completely new for me, and doing that all alone would not have been possible without them. And then meeting Jonathan a couple of years later was also a huge help. I mean, it was just crazy coincidence. We were at the same conference, and then we just hit off really well. And he was a huge help towards the end of the PhD, providing feedback super quickly for papers and also for the thesis itself. So thank you guys for your support. And the army of students, so now I reveal them. But they were all amazing to work with. I mean, I just loved the discussions that we could all have. You questioning what I'd done, you adopting the open source reproducible mindset that I had, so that we could make things that could be a continual learning process for us all. So yeah, thank you for all of your work, and I hope that I could help you in your paths, and I'm happy that our paths could cross on working on this project. And you all helped so much during the PhD. I mean, it was really a team effort in a way. I mean, I get the credit, but really, it's thanks to these students as well too. The regular fixtures of LCAV, so they were there in part 1, but they're also here in part 2. Paolo and Mihailo. I tried to find it. Look, I even said change Mihailo pick. I couldn't find another one of just him, but this is the pick I have for him. But these two are great. I mean, I had a lot of teaching experience with them. And it was Paolo's soothing voice that brought me to EPFL, as Martin mentioned, for the Coursera course. And yeah, with Mihailo just having lunches, chatting, and the time we could spend. And of course, the one who runs the lab, as Martin said, Nicoletta. I mean, where she's there. Yeah. So much support. I mean, as Martin said, maybe there was an LCAV with an LCAV. I've really had so much off of my shoulders because of your support and just your warm personality. It was just so great, the little chats that we could have. Here was a time where we celebrated my birthday, and there's a less formal, funner picture. And then, as Martin mentioned, she organized or helped organize a lot of the outings that we did, which were really, really, really fun. And we were really lucky as a lab to have these opportunities and to have Nicoletta to support us all administratively, and then also just having such a warm personality as well too. So then Nicoletta was not only in charge of LCAV, but also IVRL. So like halfway through the PhD, or maybe a bit later, we started to do activities with another lab, IVRL, which is on our hallway. So Sabine, who was on the president of my jury. And that was really cool, spending time with all you guys. Because we were a dwindling lab, and I guess you guys too. So it was nice that we could become LCAV together again. Apparently IVRL was LCAV 2 at one point. I don't know, but that was really cool, having lunches with you guys, coffee breaks, and all these outings together. I also had the pleasure of being with a lab in Paris for a few months. So Martin was super kind that after Nushka and I got married, he let me go to Paris, and I found this really perfect fit of a lab to work with. So that was really cool. So this is the lab of Sylvain Gigon, and I worked a lot with Louis, who was just awesome to work with. Yeah, and I'm looking forward to go back to Paris and maybe meeting some of those people again as well too. There were also some other interactions and collaborations at conferences during the PhD. So one was with Layla at Berkeley. So we had a lot of musings and contemplations about what are we doing with our lives and lens imaging. So those were good moments. We met at a couple conferences, so that was cool. And then Gert-Jan and Dip from Genelli in DC, we got to collaborate a bit on another software package. So that was great meeting you guys, and the way you guys could host me as well in DC. That was really great meeting you. And as Martin mentioned, none of this also would be possible without the funding from the Swiss institutes. So I'm really grateful to them. I don't know if there's any representative here, but you get a cookie. Okay, so take two. The rest of you can take one cookie. These guys can take 2 cookies. So yeah, huge thanks to that, guys. Really, I mean, a lot of EPFL wouldn't be possible without this. And of course, friends. There were some pictures there, and I'm going to break down again a bit, but this has been such a huge, huge blessing during my time here at EPFL. Firstly, with Lozak, I mean, this started with my master's, and there's a few of them here. It was such an awesome team. It was just like there was just a spirit of, okay, let's just do something, and then it was just fun. And it was amazing that we had that initial support from Martin, and then the track record. And I see Gael also in the audience, so thank you. And then also all the companies from the Innovation Park who just enabled us to do all these things for the community. And I think that is something super cool. And if you're in your bachelor's or master's, I recommend, I think Michael is here, who just started first year bachelor's, join an association. It's a really great way to complement your EPFL life and just go beyond your own self, okay, I'm grinding for my own purposes, but really it's like something for the community too. And that was something that's I'm super grateful for. I learned so much from serving and working with these people for the EPFL Lausanne community, and that was a lot of fun. And then that opened other doors for other things. So organize these other events with Thomas and Arnout in the AI Center. So these other meetups outside of EPFL, and maybe I hope to continue these in Paris as well too. So yeah, this all started also because of Surab, who I'll mention in a bit. And then when I first came to Lausanne, my first, I guess, family you could say here were Paul and Mark, so the 2 guys here. They're brothers. They had a flat share here, and then they only had brothers together, and then all of a sudden they needed someone new. I came into the picture. I was also from California, and if you know how difficult it is to find an apartment in Lausanne, it is difficult, and that California card really helped. And then these guys have been really like brothers to me. And then I just spent so much time. And then that family, that B12 family, so B12 was this Boston 12 was where we grew, or where we, I guess, grew up, but also lived together. So that grew with Heidi, Paul's wife. They have a child, Juliette, too, who's also here. And then I stayed in the apartment. We got 2 more roommates, Pierre and Flavio, and then some more people I think we saw switch before. And that was been a really cool family for me, especially I left Lausanne, I came back after COVID, and it could have been really tough for someone who's coming to a new place. And I had such a great foundation of this tight family. We spent so much time during lockdown together, and that was really cool. Some friends from the constructors, bachelor's days. Robin, I mean, we've been able to meet up quite a few times. Lives in Belgium, and looking forward to see them some more. Yeah, they've been really awesome friends that we did engineering studies together. Yeah, and then the old friends. Another, as I mentioned before, when I came back to Lausanne, having these guys visits, not Surab yet, Eloine and Lilo was such a huge help when I first came. Also, Frederica was also here when I first came back. Yeah, and with Surab, he was the guy who asked me, "There's no hackathon in Lausanne. Why don't we do one?" I was like, "Sure, why not?" And so. Yeah, these are amazing. This was when Vidit was on fire at my wedding. You should ask him about that picture. I don't think he remembers, so ask Eloine about it. And then Lilo too was probably my first friend from the PhD cohort here. So we had a lot of runs together where he'll blame me for his knees, but he's a strong guy. The Westlake Church community has also been a huge bedrock for me here. So I'm Christian, and then my faith has grown a lot here, and through the PhD, and then having these brothers and sisters has been amazing in this journey for me too. So thank you for the Westlake community as well too, for all that you've done and the support and the way I could also serve there, and then the way we can encourage each other as well too. They even let me do a hackathon at the church. So that was pretty cool. And they did pretty good. They made some Telegram bots as well too. So yeah, proud of them and hope it can continue, but we'll see. So yeah, and family. So these AB and Andrew, so my cousins, I mean, we grew up in California together. They were kind of like, I'm an only child. They were kind of like my brothers and sisters. And Jananti was such a loving aunt who made it. She's the one who made this. So thank you for supporting me through childhood and just always being loving and caring for me. For my in-laws, I mean, they live living closer by, so we could go visit them once a month, and that was just such a peaceful moment. I think that'll be the one moment where you wouldn't as often see me with the computer there. First of all, there was no Wi-Fi there, so that that helps. But then they've been so loving and yeah, I'm happy to move closer with them and then to see Elliot and Luciana grow up. Just spending time playing with them is so much fun, and to Barbara and Sivan, who've just been parents here as well for me too. A brother that I could have through Nushka and a sister, his wife. It's been amazing just seeing the kids grow and then spending time with them over the last couple of years. And then of course my parents, Ignatius and Laura. I love them so much. They let their only child, as Martin said, just go all the way to Germany and just explore the world and do so many things. And I thank them for that, for giving their most precious possession out like that. Always being supportive when I've been rebellious, and I thank you for that. And for your love and your patience. Yeah. Thanks. Should have brought some tissues. And then, as my dad said, life started with my beautiful wife, Nushka, as a married couple 3 years ago. I almost wore the same suits today. The zipper broke, not because I'm getting fatter, but because it's the clothes. But this suit I wore in the religious wedding. So, but yeah, I mean, again, Nushka has been so much for me in these last few years and put up with so much, sacrifice a lot for me to work and grind and give my time away to others, whether it's for the PhD, for Lozak, for the church, for other things, and so supportive in all this. And I'm just so happy to spend my life with her. And the light that shines in the darkness. So this is who my thesis is dedicated to. Nushka is obviously light for me, but the light for me is really Jesus. I mean, who's given me so much strength and love for so many of you. And then if I can give, like, let's say a final table, let's say phases of a PhD student. I think we all go into these blocks even after a PhD, if you don't have a PhD or whatnot. And it's this opinion of others and opinion of self. And if I talk about it within the PhD context, you can have this low opinion of others, high of others, low of yourself, high of self. In academia, it's easy to follow in the cynical box. Everything sucks. My work sucks. And I'm definitely guilty of that. Or self-doubt, like, oh man, especially who's done like death scrolling on Google Scholar, just saying, oh man, I'll never reach that. Look at that H index. Like, what have I done, Or being proud, like maybe you get something and like, oh wow, everyone's heaping the praise on you now, thinking that, okay, this was all my effort. That can be dangerous too. But for me, what confidence is, so I don't know where I think it was a podcast, I don't know where, but I didn't see it drawn and I wanted to draw it. But there's this confidence, which is really just having this high opinion of self and high of others. And I'm always jumping around this. Nushka knows this. And I try to be as much as I can in that confident box. And as I mentioned before, Jesus helps me to be in that confident box. And I'm thankful for him for the intelligence he's given me, all the friends and support he's given me here. And the thesis was talking a lot about lights, but really the Lord, Jesus, God is the light in my salvation. And then with him, I don't fear anything. I can be confident because of this, and just share that love and want to serve Lozak, want to serve in my church. And I'm so happy then I have all these friends that encourage me here too. And that, quoting another psalm, I can walk through the deepest of deeps, and then I just don't have to have any fear because I know he's with me and I'm loved, not because of what I've achieved, but yeah, because he loves me. And then he's there with me. So yeah, that's all I have. And we have the apero. So I hope you enjoy it.